Right now, more than 3 billion miles away, Pluto is quietly slipping farther from the Sun, and its thin blue atmosphere is freezing, falling, and disappearing with it. In roughly 12 years, that thin blue haze will be gone, and somehow, in the middle of that slow fade-out, the James Webb Space Telescope just caught something nobody expected to find at all, something that never should have been there in the first place. Before we go any further, if you love real science stories with no exaggeration and no clickbait, hit subscribe right now and turn the bell on, because what is happening right now at the edge of our solar system is something you will want to hear about long before the next big announcement drops. For most of human history, Pluto was just a tiny white dot. Clyde Tombaugh first spotted it in 1930, and for almost 100 years that was all we had, a faint smudge of light moving slowly against the stars. It was treated like the 9th planet of our solar system, then reclassified as a dwarf planet in 2006, and most people assumed it was a frozen, dead rock, too cold and too small to do anything interesting ever again. But the story of how Pluto was found is part of why it took us so long to understand it. Back in 1905, a wealthy businessman named Percival Lowell, who had also championed the idea that Mars was crisscrossed by canals, kicked off an extended search for a hidden 9th planet at his observatory in Flagstaff, Arizona. He called it Planet X. Lowell died in 1916 without finding it. The search quietly continued for over a decade. In 1929, a young assistant named Clyde Tombaugh, just 23 years old, was handed thousands of photographic plates of the night sky and a strange mechanical device called a blink comparator. He spent months moving slowly back and forth between plate pairs, staring for hours, looking for any one dot among thousands that quietly shifted position between two nights. On February 18, 1930, he found it. That dot was Pluto. Tombaugh died in 1997, less than 20 years before a spacecraft finally flew past the world he had discovered. But Pluto is stranger than almost anyone gave it credit for. It takes Pluto around 248 Earth years to circle the Sun once, because it sits about 3 billion miles out on a long oval orbit. The orbit is so stretched that Pluto's distance from the Sun swings between roughly 2.5 billion miles at closest approach and more than 4.5 billion miles at farthest. Pluto passed its closest point to the Sun on September 5, 1989. Every year since then, it has been drifting slightly farther away, and it will keep moving away for close to another century, not reaching its farthest point until around the year 2114. And here is the strange trick. Pluto is tilted on its side. Its axial tilt is about 120 degrees, meaning Pluto essentially rolls around the Sun on its belly, the way Uranus does, but even more extreme. So Pluto's poles swap. As Pluto moves along its orbit, first one pole catches the Sun, then the equator catches the Sun, then the other pole catches the Sun. Because Pluto is now past closest approach and moving toward farthest, the Sun stays low on Pluto's horizon. The thin nitrogen frost on the ground has less energy to lift into the air. That is one of the main reasons the atmosphere is collapsing right now, and why scientists have an opening to watch it happen. Then, in July 2015, NASA's New Horizons spacecraft flew past Pluto after a 9.5-year journey across more than 3 billion miles of space. The pictures that came back shocked everyone. Pluto was not dead. It had bright white plains of nitrogen ice in a giant heart shape called Sputnik Planitia. It had tall water ice mountains. It had a thin blue sky. It even had a thin atmosphere, made mostly of nitrogen, with traces of methane and carbon monoxide. That flyby on July 14, 2015, was the day Pluto went from a boring smudge to one of the most surprising worlds in the entire solar system. Let us walk through what New Horizons saw, because those pictures set up everything Webb found later. New Horizons came closest at around 7,750 miles above the surface. It carried 7 scientific instruments working together, including Ralph, a spectrometer that reads surface composition, Alice, an ultraviolet spectrometer that reads how gases absorb sunlight, Rex, the radio science experiment that probed the atmosphere directly by sending radio signals through it, and Lori, a high-resolution imager that took the close-up black and white frames. The spacecraft was powered by a small radioisotope thermoelectric generator, a compact plutonium heat source, because sunlight out near Pluto is so weak that solar panels would be useless. And what they found was not a single story, but a stack of surprises. Sputnik Planitia, the giant heart, was young, so young that almost no impact craters dotted its surface, meaning whatever was making it smooth had been active within the last few million years. On Earth, a few million years sounds like forever. On a dwarf planet whose surface is colder than dry ice, that is recent. Something inside or beneath Pluto was pushing fresh nitrogen ice up to the surface, like a slow exhale of ice. Around the edges of the heart were tall mountains of water ice, frozen water so hard at Pluto's temperatures that it behaves like rock. The Tenzing Montes range near the heart's edge rises about 11,000 feet above the plain. They stand like granite, held by their own stiff strength. There were dark regions on Pluto's equator and near its poles that New Horizons found were covered in tholin material, reddish-brown gunk made when sunlight breaks methane high in Pluto's thin sky, and the broken pieces recombine into a kind of organic soot. Those tholins had been falling out of the atmosphere for billions of years, slowly painting parts of Pluto's surface like quiet rust on an old bicycle. Some dark patches were thick enough to clearly change Pluto's surface color from tan to deep brick red when viewed close up. And then there was the sky. New Horizons caught the silhouette of Pluto against the sun and saw thin blue rings of haze extending more than 100 miles above the surface. Those layers of haze were made of the same tholin particles, suspended by gentle rising motion. Pluto had weather. Pluto had color in its air. Pluto had a sky that, in principle, you could fly a balloon through. You have to stop here for a moment and feel how strange that is. Pluto's atmosphere is so thin that on Earth, walking through it would feel almost like vacuum. The surface pressure is roughly 10 microbars, around 100,000 times thinner than the air you are breathing right now. Nitrogen gas is heavy by solar system standards, heavy enough to sink and hug the floor on Earth. Yet on Pluto, it drifts upward, paints the sky blue, condenses back into frost, and rises again. Pluto's escape velocity, the speed a molecule needs to fly off forever, is only about 1.2 kilometers per second. Nitrogen moves faster than that in normal sunlight. So Pluto's atmosphere should leak itself into space over the centuries. That is one of the deepest puzzles Webb helped clarify. The haze cooling Webb confirmed keeps the upper atmosphere colder, which keeps nitrogen molecules moving slower, which keeps them slightly easier to trap near the ground instead of escaping into space. Without that haze cooling, the atmosphere would probably be collapsing faster than it is. But New Horizons flew past fast. It could not stay. It kept going, and in 2019 it flew past a tiny Kuiper Belt object called Arakoth, a strange two-lobed snowman of ice about 21 miles long. Pluto was already shrinking in the rearview mirror. Scientists on Earth had to wait for a telescope powerful enough to look at that tiny, distant world from space and read the chemistry of its surface and its sky. That telescope finally arrived. It is the James Webb Space Telescope, launched on December 25, 2021, from French Guiana in South America, parked about 1 million miles from Earth at a place called the second Lagrange point, where the pull of Earth and Sun balance out so a spacecraft can sit still relative to both. Since 2022, it has been slowly turning its huge golden eye toward the outer solar system. In 2022 and 2023, a team led by Dr. Silvia Protopapa at the Southwest Research Institute pointed Webb's near-infrared spectrograph, called NIRSPEC, at the Pluto system. They wanted to read the light bouncing off Pluto and its largest moon, Charon, and break that light into a rainbow of colors the way a prism splits sunlight, so they could see which chemicals left fingerprints in the light. Webb does not actually photograph Pluto the way New Horizons did. Pluto is small and so far away that it falls into just a single pixel in most of Webb's cameras. What Webb can do, and does brilliantly, is collect the light that comes off Pluto and split it into its component colors, a method called spectroscopy. Some colors bounce back untouched. Other colors are swallowed by chemicals on the surface. By measuring exactly which come back and which are missing, scientists tell what is sitting on the surface, layer by layer, even if they cannot see the shapes. The team also used MIRI, Webb's mid-infrared instrument, which sees longer wavelengths and is good at measuring how much heat a cold object like Pluto gives off. By combining NIRSPEC and MIRI, the team mapped both the chemistry and the temperature of Pluto's atmosphere at the same time. And here is the first place the story breaks wide open. Scientists expected Charon, Pluto's biggest moon, to be a quiet ball of dirty ice, a little over 750 miles wide, around half the size of the United States, sitting in the Kuiper Belt. They expected water ice on its surface. They expected ammonia leftovers stored in cold traps. They did not expect carbon dioxide, and they absolutely did not expect hydrogen peroxide, the same basic stuff in the brown plastic bottle in your medicine cabinet, sitting frozen on a moon 3 billion miles from the sun. But that is exactly what Webb found. The light fingerprint of carbon dioxide, CO2, appeared in the data, and so did the clear signature of hydrogen peroxide, H2O2. Both were announced in a major study published in the journal Nature Communications in 2024. Importantly, this was the very first time either chemical had ever been seen on Charon. Nobody had seen it before, and nobody was expecting to see it now. Here is why that matters in plain words. Hydrogen peroxide is not some rare exotic space chemical. On Earth, our own cells make small amounts of it, and we use a stronger version in a brown plastic bottle to clean cuts. For it to sit on the surface of a frozen moon, it has to be created somehow, right there on that moon. Sunlight contains ultraviolet radiation, which is a kind of invisible, strong light that can break apart molecules. When ultraviolet light hits water ice, it can split the water into hydrogen and oxygen, and those pieces can recombine into hydrogen peroxide. So by finding hydrogen peroxide on Charon, Webb proved that Charon's surface is being slowly changed by ultraviolet radiation from a sun that is more than 40 times farther away than the sun is from Earth. That sun looks like a bright star from Charon, not a big yellow ball, but it is still strong enough to alter the chemistry of a surface from 3 billion miles away. And here's the next twist. The carbon dioxide on Charon is not coming from Charon itself. The CO2 was almost certainly locked into the minerals of the ancient protoplanetary disk, the flat, spinning cloud of gas and dust that surrounded the baby sun more than 4.5 billion years ago, and out of which Pluto and Charon both formed. So Webb, finding CO2 on Charon today, is reading a chemical fossil, a tiny leftover ingredient from the very beginning of the solar system, still sitting on the surface waiting to be counted. The Protopapa team also noticed something quiet but important. The CO2 and H2O2 signals are strongest on Charon's northern hemisphere, where temperatures are slightly warmer during part of Charon's long year. Cold traps, those freezer-like spots on a moon's surface where gases can freeze and concentrate over millions of years, are best developed near the poles of slowly rotating worlds. Charon rotates once every 6.4 Earth days and is tidally locked to Pluto, so it keeps one face pointed toward Pluto the way our moon keeps one face toward Earth. That makes Charon's polar regions natural cold traps. The CO2 and H2O2 are likely locked into those traps like marbles frozen into ice, sitting there for most of Charon's year, waiting for the season to tip enough warmth their way to thaw and shift slightly. And that is only half the story. Shift your eyes to Pluto itself, not Charon. Pluto has seasons, just like Earth, and they are extreme. Its year lasts almost 248 Earth years, and on Pluto, a single season can last longer than many human lifetimes. Right now, Pluto is moving slowly away from the Sun, and scientists have been watching its thin nitrogen atmosphere shrink. Between mid-2021 and July 2023, the bulk pressure of Pluto's atmosphere fell by about 16%, which is a huge drop in just 2 years for a tiny world. The atmosphere is literally freezing back onto the surface. This collapse has been debated for almost 50 years. Some models predicted an orderly freeze-out, with gas drifting down as the Sun weakened past 1989. Other models predicted the opposite, suggesting that heat trapped inside Pluto's small rocky core could keep some gas aloft for much longer, perhaps for decades. New Horizons gave a short snapshot in 2015 and showed that the atmosphere was thicker than expected and slowly escaping. That left the long-term question wide open. Are we watching a slow freeze-out or an atmosphere that quietly hangs on? Webb's measurements, the multi-year pressure drop of around 16% between 2021 and 2023, lean toward an orderly collapse. The gas is going down. The sky is thinning. Pluto's next closest approach is well over a century away. So this window in which we can see Pluto's atmosphere in mid-collapse is special, because if we miss it, the next chance comes long after most of us are gone. Scientists expected that, as the atmosphere thins, the few upper layers left behind would behave like a balloon, slowly losing air. They did not expect those upper layers to come in colder than they should be, by a full 30 degrees Celsius colder than older computer models predicted. They did not expect that the haze, the thin blue mist of particles floating in Pluto's sky, would be the reason why. Now here's the part that scientists say they will remember for a long time. Since 2017, a planetary scientist in California, Dr. Shi Zhang, at the University of California, Santa Cruz, had put forward an idea that many of his peers called outlandish at the time. He proposed that Pluto's atmosphere is dominated not by gases alone, but by tiny floating haze particles. These particles are created high in the sky when ultraviolet sunlight breaks apart methane, a simple gas made of carbon and hydrogen, and the broken pieces recombine into a kind of soot, similar to smog, called tholins. Tholins are the same reddish-brown gunk that gives Saturn's moon Titan its orange glow. Zhang proposed that these haze particles do something nobody had measured before. He said they heat up and cool down, and that this simple on-off heating and cooling, like a tiny radiator in the sky, actually controls the entire energy balance of Pluto's upper atmosphere. Many people thought the idea was bold, possibly wrong, possibly untestable. Then, in 2023, Webb pointed at Pluto, and in 2025 the result was published by Zhang's team. Webb confirmed the haze hypothesis directly. The hazes in Pluto's sky are cooling the atmosphere to roughly negative 203 degrees Celsius, around negative 333 degrees Fahrenheit. That is dramatically colder than the temperature any earlier model had predicted. The haze acts like an open window in a cold room, radiating heat out into space. And the way the confirmation worked is worth a moment. Zhang and his team compared two scenarios. In one model, Pluto's haze was a passive decoration that scattered light but did not change temperature. In another, the haze was an active radiator, absorbing tiny amounts of light, warming slightly, and then radiating that warmth back out as infrared light into deep space. Only the second model produced the colder upper atmosphere that Webb actually measured. So the haze is, in a real technical sense, the dominant thermostat of Pluto's sky. So let us walk through what this really means, one piece at a time, in the order scientists are still working it out in their own heads. First, scientists expected Pluto to be a simple fossil world, a small, frozen ball with a thin, passive atmosphere going away quietly as it cools. Then Webb showed that Pluto is actively chemically interesting, creating organic haze out of methane and sunlight, and exchanging material between its surface, its air, and even its moon Charon, the way Earth exchanges water between ocean, air, and rain. Finally, scientists realized the haze itself is not a decoration. The haze is a thermostat, and the room is Pluto's entire sky. And there is something else. Pluto is not the only world where tholins and methane haze behave this way. Titan, the big orange moon of Saturn, has the same basic chemistry turning methane into haze particles. On Titan, that haze sits in a thick atmosphere and makes the sky a deep golden color. On Pluto, the haze sits in a thin atmosphere and turns the sky a pale, cool blue. The chemistry is similar. The result is wildly different. Titan keeps its fog and warmth. Pluto is losing its fog to cold. Two worlds, 3 billion miles apart, playing variations on the same strange atmospheric music. That difference is now a free lab experiment for planetary scientists. Titan's atmosphere is much thicker than Pluto's, so haze particles have more time to interact with sunlight before settling out. They stay suspended longer. The haze layer is much thicker, and the sky comes out deep orange. On Pluto, the atmosphere is so thin that haze particles do not stay suspended nearly as long. The layer above the ground is far more delicate, the light comes through, scatters only partly, and the sky ends up blue. A small difference in chemistry produces a giant difference in color. It is the kind of lesson that matters for understanding other hazy worlds in our solar system, and for reading the spectra of hazy exoplanets around other stars. That is the part people tend to remember most, because it is the part nobody saw coming. Not that Pluto has haze, scientists already knew that from New Horizons in 2015. The surprise is that the haze is the main driver of how cold the sky gets. The whole upper atmosphere of Pluto is, in a real physical sense, tuned by tiny floating smoke particles that were once part of a frozen moon's sky. Now let us pause and take stock. On Earth, weather is mostly driven by water. Water vapor rises, makes clouds, makes rain, makes storms. On Pluto, weather appears to be driven by haze made from broken methane, a soot-like fog. On Pluto, the haze is doing something stronger than ordinary dust. It is the difference between an atmosphere that is slightly too cold and one that is 30 degrees too cold, all the way up in the high sky. So here's the question worth asking yourself right now. If a thin layer of haze can change the temperature of an entire atmosphere on a dwarf planet 3 billion miles away, what does that say about how tiny effects shape big systems everywhere, including here in our own atmosphere, where there are also real floating particles, real aerosols, real haze? Does that change how you think about clouds or pollution, or even the brightness of the sky on a hot summer day? If that thought made you stop for a second, drop a comment below and tell me what you think the haze story means for how we understand air on any world. And if you have not already, consider subscribing now, because the next story is going to push this strange Pluto picture even further. Now let us push. The 2024 Nature Communications study on Charon did not just drop two chemicals on a moon and walk away, it connected them. Hydrogen peroxide on the surface means Charon's water ice is being turned into a mild chemical that should not survive long on a world bathed in faint sunlight. Carbon dioxide on the surface means the early solar system left chemical fingerprints on Charon that have survived almost unchanged for 4.5 billion years. Together, those two detections mean that Charon is not a quiet frozen rock. Charon is a world with active surface chemistry, not deep geology, not volcanoes, but real chemistry in the top layer of its ice, driven by dim starlight. And the same JWST observations that did this were the ones that found the haze cooling effect on Pluto. The same telescope, the same team of scientists, the same 2 years of pointed observation. One set of data revealed active chemistry on Pluto's largest moon. The same set of data revealed a hidden climate driver on Pluto itself. Let us put numbers next to this, so the size of the weirdness is real and not just a feeling. Pluto sits about 40 times farther from the Sun than Earth does. 40 times. If you imagine Earth is 1 inch from a lamp, Pluto would be about 3 1/3 feet from the same lamp. That is how far the sunlight has to stretch. Pluto's surface temperature, before you consider the haze effect, was already around -230 degrees Celsius, about -382 degrees Fahrenheit, a cold so deep that air itself can freeze into ice. After including the haze cooling effect, the upper atmosphere is around -203 degrees Celsius, meaning the haze is the difference between -200 and -230. In a place already this cold, losing another 30 degrees of heat is enormous. Charon is about 750 miles across, roughly the distance from Los Angeles to Kansas City. That is a small world by solar system standards, but it is large enough to hold air, hold ancient chemistry, and now hold hydrogen peroxide from sunlight. Pluto itself is about 1,400 miles across, smaller than Earth's moon, and yet it has weather, an atmosphere, organic haze chemistry, and a slowly collapsing sky. And here is the part that makes this story feel unfinished. And this matters. Webb's 4 observations of Pluto in 2022 and 2023 are only the opening chapter of a long campaign. To see how fast Pluto's atmosphere is collapsing, scientists need more JWST observations later this decade and into the 2030s, when Pluto will be near its farthest distance from the Sun. If the haze cooling hypothesis is solid, the haze should also be doing something on the cold side of Pluto's orbit that we have not yet measured, when sunlight is weakest. That makes this a wonderful, slow-moving experiment, one telescope, one team, watching one distant world change across decades. We are barely past the first chapter, and we already have a strange plot twist. And that is what makes the moment we are in now feel so important. We are watching Pluto's atmosphere in the middle of dying, and we are watching it with the most powerful space telescope ever built. 100 years from now, the haze chemistry might be very different. The CO2 might still be there on Charon, locked into the same cold rock. But the chance to catch Pluto's sky in transition is something we only get once in this particular stretch of human history. Now zoom out for a moment. There is a dwarf planet at the edge of our solar system, one we officially downgraded from a planet in 2006 that almost nobody talks about in everyday conversation. That tiny world has just forced the smartest scientists on Earth to change how they think about atmospheres. It has given us a place where smoke particles in the sky control the weather. It has reminded us that the early solar system left CO2 behind on tiny moons, like a label on a shipping box, still readable after billions of years. It has shown us that even a cold, dead-looking rock, 3 billion miles away, can still cook hydrogen peroxide on its surface from faint sunlight. And here is a thought that makes everything we just talked about feel even more personal. Scientists are already mapping the haze cooling effect onto predictions for thin atmospheres around other worlds, including possibly some exoplanets far from their stars. If haze can be a thermostat on Pluto, perhaps haze is also a thermostat on small exoplanets that we have not yet examined closely. Those are not Earth-like worlds, but they are the kind of worlds that the next generation of space telescopes will see first, because big, bright Earth twins are extremely hard to find. Tiny, hazy, Pluto-like planets are everywhere. And it has done all this with one telescope, one pointed carefully at the dark, over just a few years of watching. Imagine what we will find when the next generation of telescopes is pointed the same direction. Imagine what is hiding on other Kuiper Belt worlds we have not even visited. Imagine the same kind of chemistry on Eris, on Makemake, on Sedna, on 100 other frozen worlds we have not named yet. So, two things are happening at once. We are getting the first clear picture of what Pluto is really like today, in this exact moment of its slow orbit around the Sun. And we are learning how to read thousands of other worlds by figuring out how thin, hazy atmospheres work. The same lab experiment is running twice, once on a familiar world we can name, and once on an entire universe of strangers we have not yet encountered. That is a rare moment in science, where one observation pays you back twice. If you have followed along to this point, you already understand why the James Webb Pluto story changes everything. It is not just about Pluto. It is about how easily we can be wrong about a world the moment we call it quiet. It is about how small particles in a thin sky can move a whole planet's temperature. It is about how a single piece of carbon frozen into a moon 4.5 billion years ago can still be measured today, sitting on the surface of a ball of ice, waiting for someone to notice. And that should also change how you think about our own world. We live under an atmosphere full of tiny floating particles, dust, sea salt, smoke, pollution, even natural aerosols from forests. We know those particles scatter sunlight, change cloud colors, and shift temperatures by small but real amounts. The Pluto story is, in the simplest sense, a very clear and dramatic example of particles in a sky doing temperature work. We are looking at Pluto's haze and seeing a clean physics lesson that we have struggled to fully understand here on Earth, where the air is thicker and the chemistry is more tangled. Pluto is teaching us something about our own sky by being quietly weird in a sky of its own. And that is what makes this a real space mystery, not just a space fact. The mystery is not whether Pluto exists or whether the math is right. The mystery is how a world that we treated as a frozen dead rock for almost 100 years could turn out to be a busy atmospheric chemistry lab, making its own weather, building its own haze, sharing material with its moon, and teaching us how thin skies work anywhere. Pluto earned its keep again, in the strangest possible way. If this story made you think twice about what is hiding out there at the edge of our solar system, do 4 things for me, and I will not ask again. First, hit subscribe if you are not already part of this channel. Second, tap the bell so you hear about the next big web finding the moment it drops. Third, drop a comment below answering this. What do you think is the strangest thing about Pluto? The haze sky, the disappearing atmosphere, or the chemistry on Charon? Pick one and tell me why. Fourth, share this video with one friend who loves space, because the people who enjoy these stories together are the reason channels like this keep finding time to make them. Thanks so much for staying with me to the very end. Whatever is hiding on Pluto right now, we just got the first clear look at it, and you were here for every step. I will see you in the next one.